Okay, so hi guys. So sorry for the delay. Plan to see you in booth, but however, maybe the internet connection is not stable. Plus, booth is very seldom used in Malaysia. I don't know which one is the main cause, but somehow, okay, never mind. I can record the video for my teaching of this chapter. Okay, so I'm going to teach you for chapter 5. If you refer to your book, it is a residence time distribution and flow models for reactors, right? So, okay, this is the book that your textbook. Okay, so I'm going to teach you this chapter, right? So, I will divide this chapter into, I think, maybe 3 or 4 parts. So it depends on the length of the video that I'm going to record to you, right? So this today we will do on the part 1, right? Okay. So, these are the topics for me to cover for your syllabus, right? So, we have the RTD stands for residence time distribution, and then experimental determination of RTD, the statistical characteristic of RTD, and then RTD for ideal reactors. So, you will see back all the reactors that you have learned before this batch PFR and then PBR, CSTR, okay, and then RTD in non-ideal flow models, and then design of non-ideal reactors, and then finally mixing of fluid in flow reactors, right? Okay, so these are the objectives of this chapter. So like I said just now, I divided into I think 3 parts for this to finish to cover up all the chapter 5. Okay, so the first one, you need to know what is residence time. Okay, so you will see a lot of ET in your book in this section as well. So basically, I'm using formula. It's different textbook. It's a different book from your textbook, but more or less, the knowledge is the same, but it's slightly different in terms of symbol. But I'm referring also to your textbook. Okay, right. And then the second objective is to determine ET from a tracer data. Will be given to you a tracer data and then later you need to determine this ET. And then write the RTD function for ideal and non-ideal reactors. Predict the conversions from RTD data using the non-ideal flow models. Okay. And then after you predict the conversion, you can also predict the effluent concentration. Okay. For multiple reaction using segregation or maximum mixedness models. These are the models that we'll use in order to predict the exit concentration, and conversion, right? Okay. Firstly, I normally will ask my student, okay, why do you need to learn this chapter? So okay, so maybe you are not familiar what is RTD. Okay, so it's residence time distribution, right? So why do we need to learn this chapter? Okay, so for instance, this is like a flow reactor. Let's say this is a PFR. So this is the inlet, and then that is the outlet. This is the buffer, right? So the buffer is actually to increase the mixing of the fluid, okay, of the reactants, okay, in your reactor, right? But somehow, if you look here, the one in the gray area is actually the stagnant region, meaning that the fluid inside the reactor is not properly mixed, all right? Similar goes to this kind of reactor, which is CSTR. So this is the stirred, so continuous stirred reactor, okay, and then you see it cannot reach normally. The stagnant region is normally that near to the wall of the reactor, right? So if it is a real industrial problem, you cannot see all this problem, those stagnant region, okay, with your bare eyes. So that's why we need to learn what is RTD, but so that we can know what is whether your reactors is running in ideal condition or not. Okay, so it deviates from the ideality. Okay, so that's why the purpose of learning this chapter, right? So again, what is RTD, residence time distribution? it is the time of atom spent in the reactor. Okay, so it can give you a characteristic of the mixing that occurs in the chemical reactor. For example, for the plug flow and also for the thoroughly mixed flow show different RTD. Okay, so the purpose of RTD, just like I mentioned just now, to diagnose the problem of your reactor, whether it running under ideal condition or non-ideal condition. And then you can also predict the conversion of and also your effluent concentration. Okay, you learned before that. Okay, from I think you have learned before this where okay um so before this you have learned that your CA is actually CA naught 1 minus x. Okay, this is a stoichiometric. So once when you predict the exit conversion, okay, or you predict the outlet conversion, okay, so you can also predict what is the effluent concentration, right? So so RTD it will be determined via inject tracer or time tracer. Okay, inject tracer normally is a colored or radioactive material. Okay, later I will tell you what are the characteristics for becoming the good tracer. And then the time tracer, this tracer will show you of how long the tracer spent in the reactor. So it will be recorded. Okay, so for instance, okay, so let's say this is your reactor, right? So this is your reactor, and then this is your flow rate in, this is your flow rate out. So you wanted to know whether your reactor is working in a ideal condition or in a good condition, or let's say you purchased your reactor 1 year ago, and then after 1 year of using it, you wanted to know whether your reactor is still having the same efficiency as you bought in last year, right? So what we'll do is you inject the tracer here in the feed. So the tracer must be a non-reactive species, easily detectable, okay, and then have similar properties, physical properties to those of the reactive mixture. And the most important thing, the tracer cannot absorb on the wall and also cannot react with the reactants or products or anything in the reactor, right? So, so there would be two methods of injection, will pulse input and step input. So the tracer will be inject at this point in the inlet, and then will be detected at the outlet. There will be a detector. So you will the detector will give you some results in the concentration of the tracer that have been injected, right? Okay, so the measurement of the RTD. Okay, so like I say just now, there are two types of injection. One is pulse input, another one is this one, the step input. Okay, pulse input and step input, two methods of injection, right? So let's say for pulse input, you will inject here, and then this is at time 0. Okay, so it will be detected by the detector here, and it will give you somehow like a curve. So it is over the time, meaning from t0 to t infinity. It will give you some curve. Okay, and then when you integrate it, okay, and then you put into an equation. So this is the formula for the RTD function is ET, which is CT over the integration of CT dt from 0 to infinity. I believe that previously in I think Provin have taught you on how to solve this part, the integration, right? So the integration, the numerical method to be used, okay, numerical method is by using Simpson's rule. Okay, I think that it is stated in this the appendix. Okay, you may refer the appendix. What is Simpson's rule? So this is like a numerical method. Okay, so you should, okay, in your textbook you will see this kind of formula, right? Okay, so this is the step input. Okay, so it's slightly different. Okay, so it looks like this. Okay, but the pulse look something like, you know, your, if you go for medical, okay, you can see those heart rate. Okay, that is like pulse response. Okay, so step response is something like this. Okay, so normally people will use pulse input compared to the step input, because step input have some drawbacks. It's difficult to maintain a constant tracer and large error, and it's expensive compared to the pulse input, right? So now we go to the next part of the RTD, which is the characteristic of RTD. Okay, so RTD will give you some characteristic on diagnosing your reactor. Okay, so the some of the characteristic is, the most that you will see is mains residence time. So in Fogler it will use TM. Okay, but in your book I think it will wait, I think in your book, okay, this is residence time thing. So in your book, it will use T bar. Alright, but it's actually the same thing. Okay, right. So this is T bar. Okay, and then variance. Okay, in Fogler they use sigma square. Similar in your book also use sigma square. Okay, so I think if you have taken a statistics subject before, you will come you have came passed by this term variance. It's like popular in statistics, right? And then you will see skewness, and then normalized RTD function and internal age distribution. Okay, so this is the integral relationship. Okay, so later you'll see solving ET is actually is an integral. Okay, so just now we know that ET is actually CT over CT, right? Okay, so this is means residence time. Okay, so it's important for you to determine ET first, because then only it will be used in calculating your TM. Okay, right. Okay, let me remind you again that your book will use this symbol, right? T bar, right? So for TM, instead of using TM, you use T bar. But actually later on, you will see the formula will is more or less the same. So don't worry, just stick to your book, okay? And then I will show you some example after this, right? Okay. So T bar is actually T times CT. Okay, T is your time, your injection time. Okay, so it will be from 0 to the infinity, and then the CT is actually responding to the time. Okay, over the integration of CT. So both integration can be solved using, again, Simpson's rule in order to solve the integration. Okay, right. So next is the variance, okay, known as sigma square. Okay, so in your book also use sigma square. Okay, so to indicate the spread of the distribution, you wanted to know how good is your, you know, the data given out by the tracer. Okay, so if the variance is big, meaning your standard deviation is big, meaning there's a lot of error. Okay, so commonly use okay, in Fogler normally I use this one lah. Okay, you see just now you determine your TM residence time and you determine ET. So it is like a sequence. You need to first determine your ET and then TM, then only you can determine your variance. Similar goes the one in your book. Okay, just now, okay, we have your T bar. T bar is actually is TM, residence time, right? And then this is actually is the T that you get from your data, and CT is the response from the data. I stop here. See you in the next video, for example.